Good morning, everybody. I am going to discuss your organic chemistry. Organic chemistry deals with the compounds of carbon. Or we can call it carbon compounds. To start with, I'll discuss what is the definition of organic compounds. So far the definition of organic compound is concerned, a definition before 1828 and after 1828 is different. Before 1828, your vital force theory was prevailing. What is vital force theory? Now, according to vital force theory, organic compounds cannot be prepared either in the laboratory or in industry. You cannot prepare, and it is isolated from living organisms, living sources like plants or animals, which are called organisms. That means you are not capable of preparing organic compound either in small scale, that is in laboratory, or in large scale in industry, and you shall have to isolate it. It is already there in plants and animals, that is living sources, or in organism, where you shall have to isolate it. From organism, the word organic has come. Now, this was the definition before 1828, that is vital force theory was prevailing. But in 1828, an interesting phenomenon happened. In 1828, Friedrich Wohler, a German chemist, he was trying to prepare ammonium cyanate. He took a mixture of sodium cyanate and ammonium chloride. He was expecting a double decomposition reaction to form sodium chloride and ammonium cyanate. This is the formula of ammonium cyanate. But it is continuing. But to his surprise, he got urea. Urea is an organic compound obtained from the urine of the animals. So first organic compound synthesized in the laboratory by Friedrich Ohler, a German chemist, is urea. If you are able to prepare one compound, we can prepare thousands tomorrow. Therefore, vital force theory no longer holds good, or it gave a death blow to vital force theory. You see, we had a very simple definition. From organism, the word organic has derived, but now we are able to prepare. Before 1828, it was idea that we cannot prepare. Now, what will be the definition of organic compound then? That is after 1828. It is observed that all organic compounds contain one element, carbon. Therefore, the definition is compounds of carbon, except you will find these compounds also contain carbon, but they are not organic compound, except carbon monoxide, carbon dioxide contain carbon, but they are not organic compound. Carbonates, bicarbonates, cyanides, isocyanides, cyanates, isocyanates, carbides of cations. Cations means it can be metal or ammonium. Ion cations where carbon usually combines with other elements by covalent bond. So this is the definition of organic compound after 1828, means till now. I am repeating once more. It is compounds of carbon, except you will find these compounds contain carbon, but they are not organic compound, except carbon monoxide, carbon dioxide, carbonates, bicarbonates, cyanides, isocyanides, cyanates, isocyanates, carbides of cations. I have written cations with it may be metal ion, also ammonium ion, where carbon usually combines with other element by covalent bond. So organic compounds is mostly a covalent bonded compound. From this definition, I can now conclude that from this definition, I can conclude an important thing, that all organic compounds are compounds of carbon, but all compounds of carbon are not organic compounds. This is very vital conclusion which we can draw from the definition. Organic compounds means this must contain carbon. Most of the books has written contain hydrogen, etc. It may contain hydrogen, may not contain. but carbon is a must. So all organic compounds are compounds of carbon, but all compounds of carbon are not organic compound. Now, organic compounds having no hydrogen. Most of the compounds contain hydrogen, but having no hydrogen is your carbon disulfide, CS2, carbon tetrachloride. It doesn't contain hydrogen, but carbon is a must. So we can now conclude all organic compounds are compounds of carbon, but all compounds of carbon are not organic compounds. Now the question is, carbon is an element. Why carbon forms so much of compounds? It is observed organic compounds number is very vast, very vast. So now the question is, why carbon forms so much of compounds? There are two reasons to explain. Number one, the electronic configuration of carbon. Its atomic number is 6. Its electronic configuration is 2, 4. You can find that it is either in octet state or in duplet state. That means it doesn't contain 8 electrons in its outermost shell, nor doesn't contain 2 electrons in its outermost shell. In order to attain the duplet, the octet state, let us take first. It has to receive 4 electrons. 4 electrons will receive, by which it becomes C minus 4. Similarly, to attain the duplet state, it has to lose 4 electrons, by which carbon becomes C plus 4. Such high amount of charge over a very small atom like carbon is highly unbearable or untenable. That means carbon cannot bear such high amount of charge, that is C minus 4 or C plus 4. Unbearable, untenable. Therefore, carbon does not form electrovalent bond. It will not try to form electrovalent bond. So, in order to satisfy its octet, only option left for carbon is to form 4 covalent bond, so that it can satisfy its octet. In order to satisfy octet state, it will form or share 4 electrons with other elements. That means it will form 4 covalent bond. This is called what is tetravalency of carbon. Tetravalency of carbon. For the formation of covalent bond, the energy required is less. Which is available in plants and animals. This small amount of energy available in plants and animals. Therefore, organic compounds are widely distributed in plants and animals. As you have observed, organic compounds mostly available in plants and animals, As our requirements we are able to prepare now, some of the organic compounds we are not yet able to prepare is your food material like carbohydrate, protein, oils and fats, lipids, etc. So this is one of the reasons. Its electron configuration wants that it should form 4 covalent bonds, and for the formation of covalent bond energy required is less, which is available in plants and animals. Therefore, organic compounds are widely distributed in plants and animals. This is one of the reasons. Second, carbon can combine with itself or that is called self combining capacity, or we call it catenation, is very much unique with carbon. Carbon can combine with itself, or that is called self-combining capacity or catenation, is very much unique. Carbon can combine with itself in different ways to form a straight chain compound. Carbon, carbon, carbon. We do not know where the chain ends. It can also form branched chain compounds. It can be straight chain, branch chain. It can form branch chain, or it can form ring or cyclic compound. Ring or cyclic compounds. The ring may contain 5 carbon atoms, 4 carbon, 6 carbon atom, etc. So you can find the catenating capacity of carbon is very much unique. It can combine with itself to form straight chain or branch chain or ring compounds. So these are the 2 reasons why carbon compounds are very, very vast. One is its electronic configuration, second is catenating capacity of carbon. So as you have observed, the compounds of carbon, that is organic compounds, is very, very vast. So in order to study them systematically, we shall have to classification. All organic compounds are divided into two categories. One side, all ring or cyclic compounds. Other side is your open chain, that you know, ring, open chain compounds. Open chain compound is otherwise called acyclic compounds, or we call it aliphatic compounds. It can be again 2 types, straight chain or branched chain. So one side all ring or cyclic compounds, other side is open chain compounds called acyclic or aliphatic compound. It can be a straight chain or branch chain. All ring compounds are again of 2 types. Only carbon is remain in the ring, that is called carbocyclic. Since only one type of element present, it is otherwise called homocyclic. In addition to carbon, if nitrogen, oxygen, sulfur are present inside the ring, these are called heteroatoms, and the ring compounds are called heterocyclic compounds. So one side only carbon remain in the ring. In addition to carbon, nitrogen, oxygen, sulfur, which are called heteroatom, may also remain in the ring are called heterocyclic. Homocyclic compounds are again the two types. One is saturated, another is unsaturated. Saturated is called alicyclic. Unsaturated is called aromatic. Again, aromatic compounds are of two types. Benzene and its derivatives are called benzenoid derivatives. And there are some characteristics of aromatic compound which is satisfied but having no benzene ring are called, these are called benzenoid aromatics. Better you write benzenoid aromatics. It is called other one which is non-benzenoid aromatics. Here some of the heterocyclic compound may also come. So if we will classify them, since organic compound is very vast, one side all ring or cyclic compound are there, other side is open chain compounds or acyclic compounds or aliphatic compound. Maybe two types, straight chain, branch chain. All ring compound may contain carbon only in the ring called homocyclic or carbocyclic. In addition to carbon, nitrogen, oxygen, sulfur, which are called heteroatoms, they may also present in the ring called heterocyclic. Homocyclic are two types, saturated called alicyclic, unsaturated aromatic. You might have heard the name of benzene. If benzene and the derivatives are present, that is called benzenoid aromatics. No benzene ring is present, but aromatic character is there. I will also tell you what are the requirement for aromatic compound. These are called non-benzenoid aromatics. Sometimes some heterocyclic compound also satisfy aromatic character, comes under the head non-benzenoid aromatics. So this is the classification. Now, if only carbon remain, it cannot be a compound. In addition to carbon, some other common elements present in organic compounds are, I write their name, elements present and their maximum covalent bond formed by them, covalency maxima. You must remember carbon, hydrogen, oxygen, nitrogen, extends for halogen, it can be fluorine, chlorine, bromine or iodine, phosphorus, sulfur, and sometimes metals are also there. So for their maximum covalent bond is concerned, carbon form 4, hydrogen 1, oxygen 2, nitrogen 3, all halogens, fluorine, chlorine, bromine, valency 1, phosphorus, it can be either 3 or 5, sulfur, either 2 or 4 or 6, and metal depends. There can be monovalent metals like sodium, potassium, etc., or divalent metal, calcium, magnesium, nickel, etc., or a trivalent like aluminum. So whenever you write the structure, you must see that their valency has been satisfied. Carbon valency 4, hydrogen 1, oxygen 2, nitrogen 3, halogen 1, fluorine, chlorine, bromine, iodine, their valency is 1. Phosphorus, sulfur, usually not included in +2 course. If phosphorus present, valence may be 3 or 5. Sulfur 2 or 4 or 6. Metals depends. So whenever I write the structural formula, you must see that their valency has been satisfied. Now, these are the elements present and their covalency maximum. Next, I am going to discuss the nomenclature, that is naming of organic compound. Nomenclature. You can name it by common system. Common system is called trivial name. Say for example CH4, its actual name is methane, but its common name is, either you can call it mass gas or natural gas. It is observed that the common name system is not sufficient. Common name system is not sufficient enough, to communicate the scientific ideas. Scientific ideas cannot be communicated properly by common system of nomenclature. Therefore, scientists all over the world framed certain rule to name organic compounds. This is known as International Union of Pure and Applied Chemistry. Pure and applied chemistry, otherwise called, if you take their first letters, IUPAC system of nomenclature. IUPAC system of nomenclature, UPAC name. So, since common name system is not sufficient enough to communicate scientific ideas, therefore all over the world scientists frame rules to name organic compounds called UPAC system, that is International Union of Pure and Applied Chemistry. So they have framed certain rules. So far the UPAC's rules are concerned, or UPAC name is concerned, it has got 3 parts. One is name, second prefix, which you write before the name, suffix, which you write after the name, or if necessary both. Third, numerical number. Numerical number is not required always, but it required sometimes. So it has got 3 parts: name, second prefix or suffix or both, third the numerical number. Now I am discussing one by one. So far the name is concerned, name depends upon the number of carbon atom it contains, because all organic compound must contain carbon. So name of the organic compound depends upon how many carbon atoms it contains. So number of I am making a table, number of carbon atoms, which is symbolized as small n, and the name. If the number of carbon atom is 1, it is meth. If contain 2 carbon atom, name is eth. 3 carbon atom, prop. 4 carbon atom, but. 5 carbon atoms, pent. 6 carbon atom, hex. 7 carbon atom, 8 hept. 8 carbon atom, oct. 9 carbon atom, non. 10 carbon atom, dec. You should have to remember at least these 10. If it contains 11 carbon atom, it is called on deck. 12 carbon atom, dodec. So number of carbon atoms decides the name of an organic compound. If contain 1 carbon atom, name is meth. 2 eth. 3 prop. 4 but. 5 pent. If it contain 6 carbon atom, hex. 7 carbon atom, hept. 8 carbon atom, oct. 9 carbon non. 10 carbon atom, dec. Other two I have written extra. 11 carbon atom on deck, 12 carbon atom dodec. So name of an organic compound is decided by how many carbon atom it contains. Now, next part is prefix before the name you write or after the name, suffix. Prefix or suffix. Sometimes we write both or both. It depends upon the functional group. The functional group. Sometimes we write FG in short. Functional group. The organic compound contain. What is a functional group? Now, functional group is either an atom or group of atoms or multiple bond. Multiple bonds means not large number of bonds. Multiple bonds means either it is double bond or triple bond. So functional group is either an atom or group of atoms or multiple bonds, that is double bond or triple bond, which decides the properties of a particular class of compounds. That functional group decides the properties of a particular class of organic compounds. So prefix or suffix, if necessary, both we write depending upon what is the functional group it contains. Functional group may be an atom or group of atoms or multiple bonds like double bond or triple bond, which decides the properties of a particular class of compound. Here I compound mean is always organic compounds. Next is a numerical number. As I have told you, numerical number is not required always. Numerical number is used when two or more compounds having same molecular formula, same molecular formula, same functional group, but differing in their structure. That is, structural formula is different. So numerical number is only used, not always, it is used only when two or more compounds have same molecular formula, same functional group, but differing in their structures. Numerical number indicates the position of the functional group, Fg functional group, and it should be numerically lowest. You shall have to count from two ends of a carbon chain. It should be numerical lowest. Indicate the position of the functional group. So where we use, now when two or more compounds have same molecular formula, same functional group but differing in their structures, numerical number indicates the position of the functional group and it should be numerical lowest. Now numerical number can be written either before the name or after the name or in between, but there is some restriction also. These restrictions I am writing in alkene and alkyne. The numerical number is written in between the name and the suffix. It cannot be written before or after. It is written only in between the name and the suffix for alkene and alkynes. For alkene, for alkyl halides, nitroalkanes, and here you write plural, and ethers. The numerical number is written prior, means before, prior to the name. That is, for this class, these three, for alkyl halides, nitroalkanes and ethers, the numerical number is written prior or before to the name. For rest of the compounds, if numerical number is used, I have told you it is not necessary always. For rest of the compounds, the numerical number may be written either before the name or after the name or between the primary suffix I will tell you what are primary suffix and this secondary suffix. I will tell you, and this secondary suffix. So how to use numerical number is important. Numerical number is not used always. As I have told you, for compounds having same molecular formula, same functional group but differing in their structure only, then only numerical number used. Numerical number indicate the position of the functional group, to which carbon atom the functional group is attached. And it should be numerical lowest. You will have to count from the left as well as the right of the chain. Which one is less number, that number is used. Numerical number can be written either before the name or after the name or in between. But there is some restriction in it. For alkenes and alkynes, the numerical number is written in between name and the suffix. For alkyl halides, nitroalkanes and ethers, the numerical number is written prior, that is before, to the name. For rest of the compounds, the numerical number may be written either before the name or after the name or between the primary suffix and the secondary suffix. So with this background, now I am going to discuss the nomenclature of different class of compound having only one functional group. Because shortage of time, I may not discuss the compounds having complicated system or more than one functional group. Now, we shall have to make a column for it, like that is first, it is what is class, name of the class. Class, tapare general formula, minimum, to start with minimum number of carbon atoms. Not necessarily it will start with 1, sometimes it can start with 2 or 3 or 4 like that. Number of minimum number, maximum nobody knows, which is symbolized as N. Then functional group. Functional group. Then I will write whether it contains suffix or prefix or both. To start with, let us start 1. I am discussing only aliphatic compounds, is your alkanes. General formula is Cn H2n plus 2. N is the number of carbon atom. It can be 1 or 2 or 3 like that. Functional group, it does not contain any specific, no specific functional group. It has got only suffix, no prefix. Suffix is ANE. ANE. I am giving some examples. Say CH4. It contains 1 carbon atom, therefore name is meth. Suffix is ANE. So complete name is methane. Similarly, CH3, its name is ethane. Or CH3, CH2, CH3. You can see the middle carbon atom contains less number of carbon atoms than the end carbon atoms. So it contains 3 carbon atoms, name is your propane. Or CH3, CH2, CH2, CH3, it is your butane. So this is class 1. That is alkanes. Next type of compounds, these I am deleting. Your alkenes. The general formula of alkenes CnH2n. Here minimum it will start with 2 carbon atom. With 1 carbon atom alkene is not possible. 2 or 3 or 4, 5 like that. Functional group, it contains a carbon-carbon double bond. Here suffix is ENE. I am giving some examples. CH2 double bond CH2, that is ethene. CH3CH double bond CH2, this is your propene. But it contain, when it contain 4 carbon atom, you will have to use the position. This is but 1En. You can see, if I count from the left, it is position 3, from right it is 1. So it is 1 is less than 3, and it is written between name and the suffix. CH3CH, CH3. This is but 2En. So for alkene, the position is written after second member, or the after when it contains more than 3 carbon atoms. Next class is your alkynes. Alkynes. Here general formula is CnH2n minus 2. N value can be 2, 3. It also starts with 2 carbon atoms minimum. With 1 carbon atom, no alkyne is possible. Functional group is carbon-carbon triple bond. The suffix is YNE. Example I am citing before you. Your ethine. Similarly, CH3C triple bond CH is your propyne. Like alkene, when it contains 4 carbon atom, position is required. It is but 1YNE. This is but 2YNE. So these are called hydrocarbons. Like carbon and hydrogen is there. One is alkane, alkene, and alkyne. So these 3 suffixes, that is Ane, Ane, Ene, and Yne, are called primary suffixes. Primary suffixes. And rest of the suffixes, rest of the suffixes are called secondary suffixes. These 3 are primary, and the rest of the suffixes are your secondary suffixes. The next class of compound. Now before that I am telling you, when alkane is devoid of 1 hydrogen, that means from alkane, when 1 hydrogen atom is removed, we get a group called alkyl group. The general formula of alkane we have seen, CnH2n plus 2. So the alkyl group will have a general formula, CnH2n plus 1. It can be symbolized as a capital R. Capital R stands for alkyl group. So if you will take methane, CH4, if 1 hydrogen atom is removed, it is called CH3, it is called methyl. Similarly, from ethane, If one hydrogen atom is removed, we can write CH3CH2 or C2H5. This is called ethyl. So alkane minus one hydrogen atom is called alkyl group. The next class will go is halides, compound containing halogens. General formula will be CnH2n plus 1x, or we can write Rx. CnH2n plus 1 can be symbolized as R. N value can be 1, 2, 3 and so on. Functional group is X. X stands for either fluorine, chlorine or bromine or iodine. Now this compound, so far the name is it contains prefix. Prefix is halo, if fluorine, fluoro, chlorine, chloro, bromine, bromo, iodine, iodo. Its suffix is same that of saturated hydrocarbon, that is ANE. Therefore the complete name is haloalkane. Halo prefix, this is name. Name stands for how many carbon atom it contains. Suffix is same that of saturated hydrocarbon. Let us take few examples. Say CH3Cl. This is your chloromethane. Similarly, CH3, CH2, say bromine, let us take Br. This is your bromoethane. If there are 3 carbon atoms, it can be 1, because position 1 contains chlorine. 1 is written prior, 1 chloropropane. Or chlorine atom may be present, may be attached to the second carbon atom. This is your 2-chloropropane. So this is regarding halides. The next category, let us take alcohols. Alcohols, fifth one is alcohols. Here general formula is CnH2n plus 1 OH, or we can write as ROH. You can start with 1 carbon atom, 2, 3, 4 and so on, 5, so on. Functional group is OH. Functional group is OH for alcohol. Now, it has got a suffix only. Suffix is a secondary one here. That is OL. You write alkane. This E is replaced by OL. Therefore, the complete name becomes alkanol. This is your complete name, alkanol. E is replaced by OL. So OL is the secondary suffix. Example, say CH3OH. This is your methanol, or CH3CH2OH. This is ethanol. If there are 3 carbon atoms, say propanol, you can write as 1 propanol or propanol 1. Here you have got a choice, or propane. I have told you in between primary and secondary suffix. Propane 1 or it can be CH3CH having same 3 carbon atom. At position 2 there is OH group, it can be 2 propanol or propanol 2 or propane 2 all. So this is your fifth category. Sixth one I'll discuss is your ether. Ether. General formula is ROR dash, where R and R dash may be same, or different alkyl groups. N value this side 1, this side 1, may minimum start with 2, 4. The functional group same, that of RO, R dash. Now it has got a prefix as well as. So general formula R dash, minimum number of carbon atom 2, 3, 4, etc. R and R dash may be same or different alkyl groups. Functional group same R dash. Now it has got a prefix is alkoxy. That means oxygen combined with one of the alkyl group becomes alkoxy. That is having less number of carbon atom, or we can call it smaller chain. Smaller chain means carbon atom is less. It has got a suffix same that of ANE. Therefore complete name is alkoxy alkane. This is your complete name. Complete name is alkoxy alkane. So I am giving you a few examples to illustrate it. Let us take say CH3 OCH3, both sides same. So this is your methoxy methane. CH3O CH2CH3, both sides different. Oxygen combined with the less number of carbon atom or smaller chain become methoxy ethane. Similarly, let us take CH3O. If there are 3 carbon atoms, this is your ethoxy, it is attached to position 1. So 1 ethoxy propane, because with the same you can write another structure having 3 carbon atom also. This is at position 2, ethoxy group is attached. So 2 ethoxy propane. So this is all today. We'll discuss some of the nomenclature in the next class, but the nomenclature will remain incomplete. I will proceed to some other parts. Thank you.